You know, there is a very specific kind of fatigue that sets in when you follow technology news. It's the vaporware fatigue. We've been hearing about the quantum revolution for, what, 15 years?
At least, yeah. It's
Yeah.
always just around the corner.
The technology of the future, and it always will be.
Exactly. We're promised these machines that can solve problems in seconds that would take, our current supercomputers thousands of years. We're told they'll cure diseases, crack every code on Earth, model the climate perfectly. But, well, here we are, 2026, and I'm still running my spreadsheets on silicon chips.
It is frustrating. But the reason for that delay isn't a lack of effort. I mean, the engineering challenges are frankly mind-boggling.
Well, today might be the day we stop rolling our eyes. We are doing a deep dive into a major breakthrough that suggests the wait might actually be over, or at least that we finally found the key to the locked door.
It certainly looks that way. We're talking about a paper published just recently, January 28, 2026, in Nature. It comes out of Stanford University from the lab of physicist John Simon. The lead author is Adam Shaw. And just to set expectations for everyone listening, our mission today is to unpack this specific breakthrough. And surprisingly, it's not about the processor speed itself. It's about reading.
It is. It's about light and lenses and how we actually get the information out. If John Simon and Adam Shaw are right, this new hardware design is the missing link to finally building a million-qubit quantum computer.
Okay, so we're going from microscopic atomic physics to, well, massive quantum data centers. Let's dive in.
Let's do it.
I want to start with the problem itself, because to really get why this Stanford paper is such a big deal, we have to understand why we aren't already using quantum computers for everything. You said reading is the bottleneck. That sounds almost too mundane, like the computer works but the monitor is broken.
Well, it sounds simple, but in the quantum world, reading is basically an act of violence against the data.
Okay, that took a turn. What do you mean by that?
So in the type of quantum computers we're talking about, the ones that use neutral atoms as qubits, the information is stored inside individual atoms. To get that info out, to read the result of your calculation, you need the atom to emit a photon.
A particle of light.
Exactly.
So the atom just shoots out a little flash of light, we catch it, and boom, we have our data.
In theory. But in practice, atoms are a complete nightmare to work with. John Simon really highlights this. He notes that atoms are incredibly stingy. First off, they don't like to emit light fast enough. But the bigger problem is the direction.
They don't aim.
Not at all. When an atom spits out a photon, it acts like a tiny sprinkler system.
A sprinkler.
Yeah, imagine a sprinkler in the middle of a totally dark field. It's spraying water or photons in every possible direction, all at once. Up, down, left, right. Now imagine you're standing way at the edge of that field with a tiny cup, trying to catch one specific drop to analyze it.
You're going to miss almost all of it. 99% of the water.
Exactly. And in quantum mechanics, if you miss that photon, you've lost the data. The calculation is just gone.
So up until now, how have people been dealing with this sprinkler problem?
Painfully. Very painfully. They've had to rely on sequential reading. Basically, they focus all their equipment on one atom, spend a whole bunch of time trying to trap its photon, confirm they got it, and then they move to the next atom.
Which is fine if you have, what, 10 atoms?
Sure, but we need a million. And this is where the physics just gets in the way. See, quantum states are incredibly fragile. They decay. So if you try to read a million atoms one by one, by the time you get to the end of the line, the data at the beginning has, well, it's evaporated.
The system crashes.
It crashes.
Yeah.
So that's the bottleneck. It's not that the atoms can't do the math, it's that we can't get the answers out fast enough before they forget what they were doing.
Precise. We need parallel processing.
Yeah.
We need to catch the water from a million sprinklers all at the exact same instant.
Yeah.
Okay, that sets the stage perfectly. So enter the Stanford team. What did they do differently? Did they just build a bigger cup?
No, they redesigned the entire sprinkler system. They went back to a concept called an optical cavity.
Optical cavity. I'm picturing a dentist with a laser.
Nothing that scary. In physics, an optical cavity is basically a trap for light. It forces light to interact with an atom. The traditional way to build one uses mirrors.
Mirrors.
Okay, think of the sources analogy. A funhouse mirror, or, an infinity mirror. You stand between two of them and you see yourself reflected back and forth forever.
Right, the endless hallway of me.
So in the traditional method, scientists put the atom right in the middle of those two mirrors. The light emits, it hits a mirror, bounces back through the atom, hits the other mirror, bounces back again, over and over.
So they're forcing the light to hang out with the atom by trapping it in a room with no doors.
That's a great way to put it. Yeah, it forces the interaction by repetition. The light might pass the atom thousands of times, and that works. It allows us to catch the data, but there is a massive engineering flaw with this if you want to scale up.
What'd you say?
Alignment. Building a million tiny, perfectly aligned mirror traps is just a nightmare. It's bulky, it's fragile, and the physics of it limits how close you can pack them together. You can't build a chip out of millions of floating mirrors.
So mirror traps are great for a Nobel Prize experiment, but bad for a consumer product.
Exactly. So John Simon and Adam Shaw looked at this and said, why are we relying on bouncing? Adam Shaw has this great quote in the paper. He says, it's not just two mirrors anymore.
What did they replace the mirrors with?
They didn't replace them entirely, but they added something crucial inside the cavity. Microlenses.
Microlenses, like
Yep.
tiny contact lenses for the atom.
Essentially,
Right.
they etched tiny little lenses inside the cavity right next to the atom.
Okay, walk me through the physics here. Why is a lens better than a mirror?
Think about that sprinkler again. The old mirror method was like putting up walls all around the sprinkler so the water just bounces around wildly until it eventually hits your cup. It works, but it's chaotic.
Okay, right.
The microlens is like putting a nozzle on the sprinkler. It takes that chaotic spray and it focuses it into a tight, directed beam.
Oh, I see. So you don't need to bounce it 10,000 times if you just aim it correctly in the first place.
Bingo. Because the microlens focuses the light so tightly onto the atom, they get a much stronger interaction with way fewer reflections. They took a chaotic spray and turned it into a laser-focused stream.
I have to play devil's advocate here for a second. We've had lenses since Galileo. We have lenses in our pockets right now on our phones. Why did it take until 2026 to think, hey, let's just put a lens next to the atom?
That is the million-dollar question. And the answer is manufacturing. It's one thing to grind a big glass lens for a telescope. It is incredibly difficult to etch a microscopic lens with perfect curvature directly onto a semiconductor chip mere microns away from a single atom, and then have it work at near absolute zero temperatures.
So this is a material science victory as much as a physics one.
Absolutely. It's all about nanofabrication. We finally have the tools to build things this small with this level of precision.
And because they can now direct the light so efficiently, they don't need that bulky mirror setup for each atom. They can pack them closer together.
Right, and that leads us to the hardware they built. They didn't just write a theory paper. They built a working array of 40 optical cavities on a single chip.
40. I know in the grand scheme of things, 40 sounds small. My smart fridge has more processing power than 40 bits.
Sure, but in the quantum world, getting 40 atoms to behave themselves and communicate all at once is monumental. It's a massive leap from one or two, and they have a larger prototype with over 500.
So we're seeing the roadmap. 40, then 500.
And because of this microlens design, they can read all of them at the same time. That's the headline. Parallel reading.
So we've gone from reading a book letter by letter to taking a snapshot of the whole page instantly.
Exactly. And that capability is what unlocks the path to the magic number. 1 million qubits.
I want to pause on that number. 1 million qubits. It's the metric everyone always throws around. Why a million? Why not 10,000? Is it just an arbitrary milestone?
It's definitely not arbitrary, no. It's a mathematical necessity. And to explain why, we probably need to step into the concept corner for a minute. We need to talk about how a quantum computer actually solves a problem, because I think a lot of people misunderstand this part.
I think most listeners know the basic 0 and 1 at the same time thing.
Right. Superposition. A classical bit is a coin that's either heads or tails. A qubit is a spinning coin. It's both until you catch it. But that doesn't explain how it calculates. It just explains how it stores data.
That's true. I know it spins, but I don't know how the spinning helps it find a cure for cancer.
John Simon uses a fantastic analogy here that I think finally clears this up. He compares a quantum computer to noise-canceling headphones.
Noise-canceling headphones. Okay, I'm skeptical, but go on. How does a computer wear headphones?
Well, think about how those headphones work. They listen to the outside noise, like the drone of an airplane engine, and they create a sound wave that is the exact opposite.
Antinoise.
Right. The peaks of the engine noise hit the valleys of the headphone wave. They interfere destructively.
They cancel each other out.
And the result? Silence.
Okay, I get the headphones.
A quantum computer does the exact same thing, but with answers. When you ask it a complex problem, it generates all possible answers simultaneously in a massive probability wave.
Okay.
Now, most of those answers are wrong. The computer's algorithm is designed so that the waves of the wrong answers interfere with each other destructively. They cancel each other out, just like the airplane noise.
That is wild. So the wrong answers are literally the noise.
Exactly. And the right answer, well, its waves align, they interact constructively, they amplify. So when you finally measure the system, when you read it, the correct solution pops out crystal clear because it's the only thing left standing.
I love that. It's not searching for a needle in a haystack. It's making the haystack vanish so only the needle is left.
That is a perfect way to put it. But, and here is the crucial connection back to the hardware, that vanishing trick requires a massive amount of waves to work.
Why?
Think about the headphones again. If the anti-noise isn't perfect, or if you only have a little bit of it, you still hear the static, you still hear the hum.
Right.
If you only have, say, 50 qubits, the noise canceling isn't strong enough. The wrong answers don't fully cancel out, you get a fuzzy result. The signal-to-noise ratio is just too low for complex things like simulating a drug molecule. To get a perfectly clear answer for a really hard problem, you need the statistical power of millions of qubits working together to force that destructive interference.
And now, the reading speed problem makes so much more sense. You can't coordinate the waves of a million qubits if you're reading them one at a time.
Exactly. If you read them sequentially, the delicate quantum state collapses before you can finish reading the millionth qubit. The noise-canceling effect fails. That's why this parallel reading with microlenses is so critical. It's the hardware that actually enables the math to work.
That clicks for me now. The microlens lets us snap the photo instantly, which preserves the noise-canceling effect, which gives us the answer.
Precisely.
So let's look to the future. The Stanford team isn't talking about building one giant monolith computer the size of a stadium, are they?
No. And this is where the network aspect of this really comes in. They're envisioning distributed quantum computers.
Which means what exactly?
Think of a modern data center, like one of Google's. You don't have one single superprocessor. You have racks and racks of servers all talking to each other. Simon and Shaw envisioned the same thing for quantum. You'd have chips with maybe a few thousand qubits each, manageable sizes, but they'd be linked together via fiber optics using these exact cavity interfaces.
So they talk to each other using light.
Light becomes the wiring. Because they've gotten so good at caching the photons with these lenses, they can ship that quantum data from one chip to another with almost no loss.
A quantum data center.
Exactly. It shifts the whole problem from how do we build one monster chip to how do we network smaller chips, which is a much more solvable engineering problem.
So if we get this, if the lenses work, if the 4D becomes a million, if the noise canceling kicks in, what happens? What do we actually get out of it?
I mean, the implications are massive. The source highlights a few that go beyond the usual suspects.
We always hear about encryption, breaking codes.
Yeah, and that's true, but it's kind of the boring answer at this point. The really constructive applications are in chemistry and material science.
Designing new stuff.
Right. Right now, classical computers are terrible at simulating molecules because molecules are quantum systems. Electrons orbiting atoms, that's just quantum mechanics. Trying to simulate a quantum reality on a classical chip is like trying to simulate the nuances of weather using an abacus. You just lose too much detail.
But a quantum computer speaks the same language as the molecule.
Exactly. We could simulate chemical synthesis perfectly. We could design drugs that target a specific protein without needing years of trial and error in a wet lab.
That's a game changer for medicine. But there was another application in the notes that caught me completely off guard. It wasn't about computing. It was about astronomy.
Yes, this is the wildcard application that I absolutely love. It turns out this exact technology, this ability to efficiently collect light at the single particle level, is exactly what astronomers have been begging for.
How does a quantum chip help a telescope?
It goes back to that networking idea, to something called interferometry.
Interferometry. Okay, break that down for us.
It's when you take two telescopes that are far apart and you combine their signals to act like one giant telescope. We do this with radio waves already. That picture of the black hole from a few years back, that was done by linking radio telescopes all over the world.
Right, the Event Horizon Telescope. It acted like a telescope the size of the Earth.
Exactly. But here's the catch. We can't do it well with visible light.
Why not?
Because visible light waves are incredibly tiny and fast. We can't synchronize the signals perfectly enough over long distances using, copper wires or standard internet. The timing gets off. and the whole image just blurs.
But these quantum networks use light.
Correct. If you can link optical telescopes using these quantum repeaters and these new cavity designs, you could synchronize them perfectly using quantum states. You could effectively create an optical telescope the size of the Earth.
And what would that let us see? Better pictures of nebulae.
Much better. We're talking about resolutions high enough to directly observe exoplanets.
Wait, directly observe. Usually when we find a planet, it's a shadow, right?
Yeah.
A dip in the light curve.
Yeah.
Or we see the star wobble.
Right. We infer them. We see the data that says a planet should be there. We don't see the planet itself. But with a quantum-linked telescope array, we could potentially take an actual picture of a planet light years away.
We could see continents. We could see oceans.
That is both terrifying and amazing. You're telling me we could look at a star system 50 light years away and see if there is blue water?
Theoretically, yes. It really brings it back to that quote from Adam Shaw in the paper. He said that manipulating light at a single particle level will transform our ability to see the world. He meant that literally.
He really did. Whether it's looking down at a biological structure or looking up at a planet in the Goldilocks zone, it all comes down to controlling light.
It's funny. We started this deep dive talking about computing speed, number crunching. But it seems like the real emotional hook here is about vision. Seeing the data, seeing the molecules, seeing the universe.
That's often how physics works. You try to solve a very specific engineering headache like, how do I read this atom faster? And you accidentally build a tool that gives you a whole new pair of eyes.
So let's recap the journey we've been on today. We started with the massive promise of quantum computing being blocked by the sprinkler problem. Atoms just spewing light everywhere, making them impossible to read quickly.
Right. And relying on clunky mirrors to catch that light was just hitting a dead end.
Then comes the Stanford team, John Simon, Adam Shaw, and their colleagues. They reimagine the optical cavity. They toss out the mirror-only approach and install microlenses. Tiny contact lenses for atoms.
Which focuses the light, enables parallel reading, and lets us scale from 40 to 500 and eventually to 1,000,000 qubits.
Which finally allows that noise-canceling math to work, solving problems we can't even touch today.
And as a bonus, gives us a telescope that might let us see an alien ocean.
Not a bad day's work for a microlens.
Not bad at all.
For the listener tuning in, it's easy to get lost in the jargon of superposition and qubits.
Yeah.
But the real takeaway here is that this is moving from theory to engineering. They built the hardware.
That's the key. This is a practical path forward. It's no longer just equations on a blackboard.
But before we sign off, I want to leave you with a thought. We talked about that telescope concept, using this tech to see things that have been, mathematically invisible to us until now.
Right.
It makes you wonder, if we are just now figuring out how to control light at the level of a single particle, what else is out there right in front of our faces, passing right through us, that we just haven't built the right lens to see yet?
That is a profound question. The universe is full of information. We're just learning how to read it.
Something to chew on while you go about your day. Thanks for diving deep with us today. Stay curious.
See you next time.